So it's a slightly different perspective than the talks you just heard so far this morning. So the main title is Planning and Learning Under Uncertainty, Theory and Practice. That sort of is a catch-all for many of the things I do in my research. The sort of subtitle then is Autonomy for Aerospace Applications. And I'll be giving it from a very specific perspective, which has to do with UAVs, which is the work domain I've been doing for the past 17 years or so. So again, I'm at MIT, and this is work representing many of my students over the past 10 to 15 years. As I mentioned, there's been a lot of interest, and I'm sure you're aware of sort of UAVs and sort of a UAS, as we call it more globally, the unpiloted autonomous systems, which is the politically correct way of saying that. I have worked for many years, and you know, if you're in the U.S., you end up working with the DoD. This is sort of the classic picture of the multi-UAS going out doing a mission of some kind. Typically ISR in terms of inspection, surveillance, and reconnaissance. But at the same time, there's been an awful lot of interest from the commercial side. And you saw some of them already in some of the presentations, but things of the form of infrastructure, agriculture, and then of course the ubiquitous real estate inspection / package drop-off, which is the new thing a lot of people have been doing. Or thinking about. So I show this picture here. It's a cheesy version, I think, of what you've seen in the previous two talks, which is more on the weather mapping side of things, which is an understanding of how to get that higher density data that I think you guys are describing you'd like, which is not just relying on the satellite imagery, but using that to populate and begin to answer the question, where should I go get further information to perhaps, in this case, this is sort of the Western United States, where might I go in the Pacific to collect additional information to help me understand what the weather will be like in the future, we'll say at Stanford while I was doing this work, sort of 3 or 4 days in the future. So those are the kinds of sort of aspects, and many of these pictures, in fact, when I was thinking about giving this talk, these are slides or pictures I would have shown on slides back in sort of 07, 08. You know, this was sort of the future. This is what everybody envisioned would sort of, we'd be using UAVs for. Of course, about that time, things got very hard in terms of flying UAVs. If you sort of track the policy and the legal issues back in 05 and time frame, it was sort of people weren't asking too many questions. It was a little bit ambiguous, but you could still fly outside. It became very clear you couldn't. We started flying inside, and you'll see what the implications of that are in a second. But the result is that recently now, both the FAA has come out with 2 major changes in the past couple of years that had significant impact, and as a result beginning to free up a lot of what you're seeing in the package delivery discussions and things like that. So that's sort of the policy aspect is going on in the background, and it has an important pieces, but the other piece that's huge and has occurred in the past 10 years, and when I look back at some of the clunky equipment that I was building and flying back in 04, it was really kind of crummy. And what's changed in the past decade has been a significant miniaturization of the devices. This is an Intel RealSense. That's much larger than it physically is. The device is about the same size as my pen. It comes out of the RGBD framework. It's the same type of thing that Microsoft pioneered with the Kinect sensor that we all use on our games, playing around in our living rooms. But this is a much smaller version of that, very powerful device, and gives you a point cloud of what's out there. Outside works to about 10 or 12 meters, and is a field of view of about 70 degrees. So awesome device for something that, this device actually weighs less than the USB cable used to plug it in, to give you a sense of how light this thing is. Now what else is happening, and this is a little bit dark, but if you see all the self-driving cars that are out there and they all have these little silver bubbles up top, those are the 3D LiDAR. What most people don't know is that those things are worth more than the cars. Each one of those is worth on the order of $10,000 or $12,000. The sensors that people are putting on these self-driving cars easily double the value of these cars. The cost of those is coming down dramatically. I'll show you a picture in a second of the kind of information we get out of them. The other thing, of course, is if you track the technology, NVIDIA is coming out with all kinds of different new GPUs and engines that can be used to really further the computational horsepower, and basically you can now put a supercomputer in the back of your self-driving car. And then of course all the technologies that I'm sure various people at this conference would talk about in terms of the different techniques that can be used in terms of deep learning that are coming out. So you've got sort of new sensors, miniaturization of those sensors, and then some of the advances on the algorithms, put all that together in a package, and you start getting devices that now become quite capable. This was something we did in the Grand Challenge, so this is now approaching a decade old, but I show this primarily to give an indication of sort of what is happening here. We're a self-driving car down here, there's a robot. Here's an image of what you would normally see. If you look carefully, you can see another robot just pulled up here. It's that thing over there. You can see a couple of things you see here. One is the self-driving, like the LiDAR data. All these lines are many, many rings of laser that are coming back. And it's tons and tons of data. We're collecting more than gigabytes per second here. But what's challenging when you look at it is to actually understand what's going on. You can see actually people standing, well, this is a house, this is a house. So when you know how to interpret them, it's not so bad. But in here, we're trying to pull out things like curbs. We're trying to figure out where the road is, where's the line. But you're also trying to figure out what the other cars are. So this isn't just an understand the static image, it's understand the entire dynamic world and then map it. So this is the way things were a decade ago in terms of technology. It was very clunky. The box that was generating all this data, the thing on top of the roof was about the size of a Kentucky Fried Chicken sort of family bucket. Very big, $150,000. The devices now, when you see them on the cars, about yay big, they're only $12,000. So the cost has come down, but the data analysis issues is still the same. You're still getting data coming in like this, and we don't necessarily have a big data problem, we have a streaming data problem. But if you don't start analyzing a streaming data problem in real time, then you have a big data problem, okay? And our big data problems are there's no value, well, there's very little value to take this robot, drive it around, and collect that data, then go sit down and analyze it. I mean, it's useful to understand how things might behave tomorrow, but that assumes the stationarity of the world, right? Which we do typically have to assume, so you can learn things from that. But this is a robot that has to exist in that world. It's real-time processing. We're collecting data, and our planet is running here at 10 hertz. We have to be making decisions at that rate. Not all decisions need to be made at the same rate, but we need to be doing learning and planning at very fast rates and understanding the world at those fast rates. So it's understanding all that data and making sure that you can actually get it to the point where you can make decisions. So the euphemism data decisions is sort of what is key in all this work. Now, that's sort of part of the image of the way things were. If you go and ask the UAV companies, what are you doing now, right? Well, this is one of them. Skydio came out of an MIT startup, and basically what they're building is a UAV where it says sport tracking. It's no longer a selfie, I'm standing in front of a bridge. It's me biking down a path. So you just buy a quad and it flies along behind you. And now you get awesome pictures of you doing fantastic things on your bike. And if that's not enough, then you can buy one that it'll just track you skiing, and you say, here I am, I'm the blob in the snow, track me, and off you go, and then it does that. Of course, if you want to make money out of it, you got to find some way to monetize it. What Airware is doing, another startup coming out of MIT, is actually doing the poaching trade, which is basically figuring out a way of figuring out where are all the animals and or where are all the people in this environment. It involves a lot of searching, a lot of tracking of objects. Unfortunately, this movie takes a while to come up, but it's sort of explore a world, figure out who's in it, figure out who's supposed to be there, figure out who's not supposed to be there, and then figure out the people who are not supposed to be there, what are they doing. There's also different aspects of search and sort of rescue. I picked up on this one just simply because it's a very, very cool capability that NVIDIA shown recently. They were just flying through a forest for a kilometer, which gets to some of the technologies that I'll talk about in a second in terms of GPS denied nav. One of the things that's interesting about all this work, and I'll go back to maybe this one up here, recently Skydio was, actually I have the same problem, I can't send my mouse, I don't know where I am. They were at MIT and they brought the quad out and they hold it in their hand, they throw it up in the air. It's very cool. You're in a room like this, they just throw it up in the air. And it takes a lot of guts to, in a room like this, just take a quad out of your pocket, throw it up in the air, have the thing stop, spin around, point right at you. And they're just sitting there just looking right at you. And if you go and buy one of these DJI machines, I bought one recently, the Spark, it's great. It's very cool, but I don't think people understand the complexity of what's involved. Let's think about this for a second. I take a quad, throw it up in the air, there's no idea where it is, there's no GPS, right? And I would argue that GPS has made us quite lazy as a community over the past 20 years. We're now doing GPS denied nav in a room like this, there's no sense of GPS, it's figuring out where it is able to, rock solid, locks on with the camera and it can see me. Now I can start waving at it, right? Right, so not only has it found me in the world, it's actually found my hand. It's seen what my hand does. The motion of my hand means a different thing to that robot. That's very cool. It's doing all of that tracking, all of that understanding, and then interpreting, right? The planning is probably not that hard in terms of what it has to do. What's interesting about this one, when Skydio brings it out, is they actually show snippets of video. Everybody does the same thing, because the robot's sitting there staring at you. It's kind of a little bit unnerving. And everybody finds a pillar and then runs around it, and then tries to hide from the robot from the pillar. And what's the robot do? Right? It doesn't just like sort of slam into the pillar, which is what one thinks. It flies around the pillar, right, and then sits over there and stares at you from the other side, because what they're actually encoded in it is not just track the person, but track the person in an information valuable way, which is get the best perspective on that person. And that isn't like come right at you and follow you around and then whack into stuff. It's figure out where to go and what they're doing. And this is, you know, as I show in the video here, that's all taken to the dynamic extreme. And so this isn't just blindly follow that blob, it's figure out where to be to get the best image of the person doing that. And so that's monetizing the information of sport, right? In the sense of, I mean, that's how the company is eventually going to end up making money. So it may not seem like it, but these are kind of real world problems, right? I mean, they're basically, you know, they're commercial. There's many more of them. Clearly things like package delivery, there's a whole issue of, well, you know, where's it got to go? How am I going to get it there? How am I going to land? How am I going to make sure I don't hit any wires? How to make sure I don't hear any little kids running around on the backyard? Because every time there's a robot, kids love them and they just run towards them. And you want to instill the exact opposite of that, which is stay away. I have a lot of spinning parts, right? So basically you'd like to be able to solve you know, demonstrate autonomous solutions for those kinds of problems. The key word here, reliability, it shows up a lot in these devices. You often see, and you'll see this with some of these machines. I noticed this recently, I was flying around in my house. These things work very well in a very narrow set of conditions. If you move off those conditions in terms of either mechanics and or the environment they're supposed to work in, mine ended up just glued against the ceiling trying to drill a hole. Basically it's very hard to then figure out what you're going to do next. So the kinds of challenges we look at academically are dynamic non-stationary environments. So there's many other things going on in the world. Non-stationary, dynamic in the sense they're moving, non-stationary in the sense they might actually be changing their mind. So you'll see, although I talk about aerospace, I'm somewhat vehicle agnostic. I do a lot of work with self-driving cars. And so the issues I'm describing here, of course, have to do with pedestrians. They keep changing their mind. They're doing one thing, they're doing something else. They're all over the place. Very hard to predict where they're going to go. Persistent operations, right? You want to make sure you can handle the failures, operate in sort of integrated states. So in that particular situation, the kinds of learning you'd be thinking about would be perhaps as the vehicle itself. So the vehicle capabilities are changing, can you track them? If the actual vehicle dynamics are changing, can you track them, can you understand them? Everything has to be done online, sort of in real time. It doesn't necessarily have to be on board, but it has to be fast. And then the certified verifiable performance gets you to the point of, do you actually really understand what this thing is doing? Okay. So as I mentioned before, you know, when you think then about if that's the high level of what you'd like to accomplish, the capabilities then come into issues like this. So you really need improved navigation and perception. The distinction between these words are navigation is where am I, perception is where's everything else. Okay. And so I use perception to look out, and navigation is to try to figure out what I'm doing. You'll find overlap between the sensors. I can use the same sensor, like a camera. I can use that for navigation. I can also use it for perception. But one of the things that's happened as you move into the different domains, we've been somewhat forced. GPS denied used to be a problem type that people said, well, you know, we'll work with GPS, which we did for years and years and years. You begin to realize how fragile that thing is. It's great when it works, but you go in an urban environment, clearly if you go indoors, it's very, very clunky. But if you're just trying to do bridge inspection, get anywhere near anything, immediately you should just assume GPS is not going to work because it's much safer. So you're really there looking about the resiliency of the sensing, and so you're probably better off to assume you don't have GPS, and if you get it, then use it. But don't assume you have it and then try to fix the problem. Just assume you don't have it, and if you get it, fantastic. Okay, and that's the much better way around. So you'll find now that people are going GPS denied as the traditional solution. Whereas before it used to be the non-traditional solution. It was always the stretch goal. Now I would just assume that it's the way things are going to be. And it's to the point, we've already talked about cell phones in space, but this is cell phones on quads. That basically you just don't bother with the electronics of a quad, you just stick propellers on a cell phone and you'll then get a quad. And then basically this is what Qualcomm does. So you typically think of Qualcomm as making the electronics for most of the Samsung phones. But basically they've done a ton of work in understanding sort of the three-dimensional space. They're flying, this was done at one of the shows. So they basically brought in an artificial three-dimensional space they could fly through, and they're just showing how they're mapping that and understanding it. This is all done completely GPS denied. So this is, from their perspective, sort of a way to utilize, they want to sell you chips, but they're thinking about how to move in the direction of, different aspects of using in this particular case, deep learning to do the navigation and perception. So that's on that end. So faster processing and response to the measured data is sort of the goal there. On the planning side, you have to deal with the fact that there really is just a lot of data here. There's a lot of data, but it also tends to be fairly corrupted and noisy. And so going back to I mentioned before about the grand challenge, that was really my first exposure to the difference between planning, assuming all the information is going to be given to you, and really understanding where it was coming from and how noisy it was. And in particular, in that case, of the number of false positives that we're getting in terms of detection. So you have a car driving along, and if you keep seeing, and the perception system keeps seeing things, and keeps reporting there's a problem, you have to figure out as a planning system how not to be overly sensitive to that. And so that was just the basics of sort of understanding that. The beginning is understanding that type of problem, but basically just trying to understand how to embed and account for the stochastic and non-stationary dynamic environments in the planning system. Again, on the long duration side, there's both a mechanical side, electromechanical side. So you'll see people going off and doing, we've done battery chargers, battery changers, people have done hybrid, people are going propane, hydrogen, whatever it is you can put on board a quad to get long distance flights. But all that does then is enable you to fly longer. You then got to address the question of, well, how do we get smarter? And this is really the thing about the autonomy is you often see autonomy done in a lab where I do an experiment and that's it. I make a video and that's the video I put on YouTube. The point is that autonomy means you could do it over and over and over again, and it could be very reliable. And that's the key. And so there you need sort of all the adaptation and learning in terms of adapting to the world. You have to be able to sort of fuse and accumulate data over the entire team, but then also be able to sort of incorporate context for future missions. So if you understand how the environment has changed from one day to the next, perhaps you can use that to improve the rate at which you can do learning. And again, obviously, in terms of, I mentioned security and certification come up. This is essential, as you'll see in a second, for some of the learning-based techniques. It's just sort of key for some of these challenges. So I try to highlight here what we list, or when we think about what kinds of things we're working on. These are the issues, these are the challenges. The main issue is a lot of planning systems you go off and look at. I mean, you'll see lots and lots of people doing planning for their career. They're almost always based on models, and even the ones that they call model-free are based on models. The model in that case is the data, and the point is that in almost all of those cases that the models are wrong, which means you need to be able to understand what's wrong about it, capture that error model, think about robust planning, and then of course, that might have limitations of performance, so then you start thinking about moving beyond that to do online adaptation and learning. So we mentioned before about the fact that navigation data tends to be noisy. And for any system I've ever built, the first thing that breaks is the network. So I don't know if that's been your experience, but radios, anytime there's a radio involved, and I often have multi-agent systems that are communicating, you basically end up with a situation where you'll just have just an inability to move data around as quickly and as well as you might have thought. And that many of the theorems and algorithms you'll see people write about don't typically understand just how complicated that process is. So in terms of challenges, it gets to the point, I mentioned the word representations. Again, this is an issue where as you're collecting all this data and you're making these models, you've got the models of the world, there's the policies that you're building in terms of planning. All of that can be learned, but you need to understand how you're effectively going to be representing that. And part of that representation needs to capture the uncertainty you have, and you need to be able to map between different representations. And the reason for that is that basically the choice of the representation using ends up being task dependent. So to give you an example, oftentimes when we do planning, we're thinking about a very spatial representation. Where is stuff? In a sort of three-dimensional space. That's what I'd like to know. And that ends up looking like a sort of an occupancy grid. So it's like I know all these chairs are, and I know exactly where it is. I can plan around them. That's very useful for me, but it scales horribly, right? And so as you have a big, large dimensional problem and you're flying around for a while, and if you write everything down as an occupancy grid, it just does not scale. So the guys who work on the mapping and the understanding of how to represent what's in this room or what's in this world, they like to use graphical models. The problem with those is they're very lousy if you come in and say, well, I want to do planning. I want to understand how can I fly through stuff. Well, they can say the relationships between things, but I don't know what's inside. I don't know if they're an object. I just know where all these features are. So that's an example of a situation where you have the best representation for the two problems you might want to do, which need to be able to talk to each other, actually end up being sort of opposite ends of the spectrum. So there's a lot of complexity in terms of computation and sample complexity. This is sort of how much data you need. We get a lot of data, but we don't often get the right kind of data. And anytime we're doing the planning and learning, it ends up being high dimensional. I mentioned several times about the certification. One of the pushbacks that we get a lot on the use of deep learning in the field of aerospace is they're very risk averse as a field, partly because there's big objects flying around doing important stuff, and they're worth a lot of money. There's almost, even though we mention autonomy, it's always semi-autonomous. There's almost always a human in the loop doing something. They may be messing it up, but they're almost always there. And what's important is that they be able to understand what the autonomy is doing. And it turns out that people write about this, but there's a need in both directions. Does the autonomy understand what the human's thinking and doing? And does the human understand what the autonomy is thinking and doing? And this gets very difficult when you have a lot of learning going on and on board a system. You need, the word transparency shows up, right? How transparent is the learned system to the human? And then quite frankly, until that issue is resolved, I imagine you're getting quite a lot of pushback on the deployment and utilization of technology of this type. So just a perspective, I mean, I'd be amiss if I wasn't to say that people have been working on this type of thing for a while. This is a colleague of mine, Gersh. They stuck a wing on an airplane and then ripped it off simply to show that they could. So the point is that they've been learning how to fly in degraded situations for a long, long time. But this is sort of, about 7 or 8 years ago. What I'd say the big difference in the recent world, or recent time is, if that's about the eco vehicle, it's all about me, right, as an agent, how are things going, right? How do I learn to fly better, right? But recently it's changed to what's going on. It's more about the outside world. So, as a student, as an early professor, I was sort of down here thinking about that. And in the past 10 or 15 years, I've moved to this way. So it's less, less about where am I and much more about what's going on outside. So much more focus on the perception, the navigation. And so, but even further than that, the questions go into understanding things that is not just about what's out there, it's what is it doing. So it isn't just a question of where is stuff, it's like what is that stuff? So you get in, if this is a mapping problem, this is a semantic mapping problem, and now you're getting into the intent part of the semantic mapping and trying to understand that next layer of depth. But none of these things are directly observable. I mean, you might be able to stare at, I can maybe do the mapping with a laser. The what, I can maybe do classification with a camera, but the how is typically not directly observable. So this is something that has to be inferred either by talking with other agents, looking at longer timescale data, and then trying to figure out on that deeper scale what exactly is it that's going on. Of course, the ultimate goal here is people describe it as the scene understanding, right? You're getting to the point where you as a robot show up and you just understand what's going on. You're immersed in it, you understand it, you get it, okay? It's not a case of like, now I'm gonna drive around mapping everything and seeing where it all is and then figure out what we're all doing. Maybe start interviewing you and asking you how you feel and stuff like that. It's just something that's known and understood. Let's see, do I have any sense of how much time I have left? Because I don't. 5 or 6 minutes, awesome, okay. I'll give you some examples of, so in a representation question, in this particular example, we have a robot trying to fly from point A to point B, and then we just reserve the right to insert all kinds of stuff in the room. And this is a case where the robot knows navigation almost perfectly because of the indoor system we have, but has basically no knowledge on the perception side. It's going to open its eyes basically and then see stuff like right in front of it. And it's flying very quickly on the scale of this distance, right? That basically has about half a second to make a decision. So basically you get to a representation question, which is how are you going to represent this world? The key question here is computation. So basically what we have is a pipeline that gets you from data to decisions, okay? And so we have data coming in the form of the three-dimensional image, which is this picture down here, and you see this stuff. Now you could take the process of saying, okay, I saw stuff in the past, let me fuse this all together in a big map, and you end up getting a big map that looks something like this. This is what a giant occupancy grid would look like. That basically it's a nice way to fuse things, you have a good understanding of the world, but typically that fusion process just takes too long. So what we did was basically cut down to, well, let's just go based on the simple image of what's here. This is literally it. That'll be the image, and you're making an instantaneous decision of what should I do now based on that image. Very approximate, but based on the choice you have to make in terms of what representation you're going to have to make that intelligent, instantaneous decision. And that's the trade-off between computation time and knowledge that basically we had to make. There's still a mapping process you run in the background, but basically you have no choice but to try to move forward and make decisions as quickly as you can. In the interest of time, let me see if I can run both these at the same time. So this is it, just booting back and forth. It's a full dimensional thing. Keep in mind, it's not seen any of these objects before in the room that it's flying through, and so it just comes right at you and does things like that. This is the camera that you mentioned before, the real sense. It's just a little one sitting there. It's looking about 3 or 4 meters in front in the space. So again, a lot of things that it sees and is surprised by, but basically it's able to figure out what to do in terms of decisions. So slow flight is easy. The question here, some of the questions we've seen before today is the question comes down to what needs to be known, how well does it need to be known, and how fast can it be computed, okay? And that basically when you are making the kinds of representational choices, this is the questions that you need to think through. It's a question about expressivity. How well can I express what's in this world? In this particular case, there isn't much we need to do. But basically, we don't have a lot of computation. We're trying to do this in about 5 milliseconds. This thing is basically flying like the Millennium Falcon. It's just sort of doing stuff like this. We get up to about 700 degrees in roll per second, and so it's just knife edge sort of flying like that, which is about the only way it can respond. Because keep in mind, the dynamics of this vehicle are actually quite slow, so in terms of how quickly it can actually influence where it's going to be. So that's at one level. At another level, there's a lot of interest in the intent inference. So of course, there's the self-driving cars, there's the delivery vehicles. What's hard about these problems is that basically there's all these other objects in the world, right? These other people, they're annoying and in the way and tend to keep changing their behavior. So when we're driving around in our building, there's a lot of people there, and we've got to try and figure out what it is they're doing. Now, this may not look very aerospace-y, but the point is that if you were 2 airplanes flying like this and you were trying to solve the air traffic control problem, it's basically the same issue. So traditionally, this is done with a ground-based radar. In the future, they're thinking about having systems that each communicate. But in the far future, right, you would actually be thinking about on the own ship, I'd sit there with all my lasers and whatever, and I'm looking out in the world and say, what else is out there, right? And basically, if there's an intruder, what are they doing and where do I think they're going to go? This is the key part here is the uncertainty in the intent, the uncertainty in the path. Basically, it's the very rapid understanding of the world in a multi-dimensional setting. Where are they going to be? So in the interest of time, I won't dwell on the details, but basically this ends up being a problem where I just don't know where other people are going to go. And what's the whole point of this slide is simply this is a very high-dimensional learning problem. Okay? And if you're faced with a high-dimensional problem, you go off and do a lot of planning, but then it's all model-based and the models are wrong, so how do you account for all that? And of course, this is the eye chart of the difference in the techniques. The challenge typically is you just don't want your robot to freeze. This is sort of the traditional way of doing things. You'll just get stuck. You'd like to have a situation where you can negotiate your way through other agents, very computationally difficult. You want something in the middle ground where you're interacting with the other people, but in a way which hopefully is done cooperatively. So let me just show you. The approach we've taken, probably not too surprising in this community, is a deep learning approach. Why deep learning? This is the question I ask my students every time they come into my office and say, I said the answer to every question cannot be deep learning. Right, there's some things we know how to do, right? And if we do, then do them that way. If there's things you don't know how to do, then fine, talk to me about deep learning. The challenge in this particular case was the very high dimensionality of the learning problem that they had to figure out. And the key part was to figure out not just the sort of the future cost, which shows up as the value network, but also they wanted to have a policy so they have both pieces, and that basically they're encoding both of those. And again, it's unfortunate I don't get to see it. Let me just show these videos. These are not encoded. This is sort of totally emergent. I hate the word emergent, but it's kind of cool that it emerges. Right? You take a bunch of agents, you drive them at each other and say go, and they actually learn how to go around each other in what looks like a fairly traditional rotary. And there's not many parts of the country would know what a rotary looks like. I think you guys do. We have some in Boston, so we know what they look like. But this is, again, not encoded. It actually behaved that way where they did the crossing. This is, again, them figuring out how to cross. It's sort of nice, but what's nice is they learn how to slow down, give way, back up a little bit, not kill each other. And I knew I was going to run out of time, so what I did was actually highlight one. We take this into what's called the wild. I love robots in the wild as a euphemism for it's our building. But basically, here's one particular situation I think is great. The lady's just at the coffee station. She went over here. She bought her coffee. She comes over here with a cup to fill it up. a robot was trapped from a bunch of guys over here, had to go around the pillar this way, and now there's the lady stopped and got her coffee, and so we just sit there patiently and wait. So this is actually something that to learn how to do, which was to not nudge right up against you and push you out of the way, which is what a fairly traditional robot would have done, but actually figured out how to wait and not kill you. Okay, so I clearly have way more slides than I was supposed to make, but let me show you, is it 1 minute now? Yeah, okay. So what I missed was all the multi-agent stuff, and maybe let me just say for 30 seconds what the issue is in multi-agent. Everything I talked about is single agent. I do a lot of multi-agent work. What's the issue in multi-agent learning? You've got a lot of people, a lot of agents in the world doing unsupervised learning. They're learning and understanding the world with their own labels. You then bump into another agent that's learned about the world with their own set of labels. The question is, how do you get the label merging and get the two to work together? So one of the things that I'd say is very big academically in the field is the area of active perception. If you guys describe your sort of forward paths, if you collect a bunch of data, you do a bunch of analysis, do a bunch of learning, the active perception is you do that path forwards, but then you go backwards and you say, okay, but hold on a sec. If that's the way I'm going to analyze all this data and get information out of the data I collected, then what data do I collect to get the information that I want? Okay. And so that's the planning problem that we work on a lot in the like kind of academically. And so when you'll see a lot of people talk about this as a key concept, it's sort of based on a lot of sort of information-based planning, value information. These are the words that show up a lot in the field as sort of the kinds of things people are trying to do. One of the things that's becoming more clear is that when you talk to these UAV companies, like when the guys left MIT and said, I'm going to go form a startup, when they left, they thought they were doing a startup building an autopilot. You talk to them about 5 years later, they realize they're in the information gathering field, okay? If you're building an autopilot, your company's going to sink, okay? There is no commercial value in building an autopilot. The value in having an autopilot is you build an autonomous vehicle that can do something robustly, that collects information. Then you go back to the active perception, which is what information do you want? Let me figure out how to get that information for you. If I can get that information for you more efficiently than someone else can, then I have an economic product I can solve. And that, I think, has been the sort of autonomy is the enabler of this. But I think that's been the revolution. You do all this work building autonomy, then you realize what it's good for, which is actually the economics of information gathering, because that's where the money is made. So anyway, thanks to all my funding agencies. I hope I listed them all. I always hate putting a list because there's always, I should have put ... but there's always a chance you lose one off. Anyway, hope you enjoyed the talk and give you some insights on the kinds of things we work on.